think I got everything set up here. To keep an eye on the audio, I'm not sure how long my batteries will last. I think I have an hour at least, so after an hour I should go and, you know, change the batteries or whatever. So let's see here. I think if I remember where we were, we talked about tangent space and normal space for Euclidean you know, manifolds. And so next I was going to talk about optimization of functions of several variables. And before I do that, though, I really should give a quick review or perhaps introduction to the theory of quadratic forms on Rn. And so I'll do that to start with here. Anyway, first let me pray. Dear Heavenly Father, we thank you for this class. I just pray that you just guide our steps today, help us to glorify you in what we do, and just please give us clear thinking today, Lord. Your name I pray, Lord Jesus. Amen. All right, so let's see. What is a quadratic form? So basically, it's something that has a formula like this: q of x equals to the sum over, let's say, I and j equals 1 to n of, oh, I don't know, qij xi xj. Maybe that's not quite right. No, that's right. So this would look like what? This would be like, you know, q11 x1 squared plus what? Plus you got like a q12 x1 x2, and you've also got a q21 x2 x1, right? And you got like a q22 x2 squared, and finally eventually you get like to your qnn xn squared, all right? So anyway, this is, I don't know why I've written just these terms. My point is that there is a sort of a natural a way, you can assume without loss of generality here that q12 is equal to q21, you know, to make the formula nice. I mean, in principle, you could make q210 and q12 whatever it needed to be also, but it's nicer if we look at this as the vector x transpose times, let's say, the matrix of q x, all right? Because if I do that, and if this is in fact a symmetric matrix, because if I do that, then, well, then it's a symmetric matrix, and symmetric matrices are super nice, right? So like, for example, one, we could have, you know, q of xyz equals to x squared plus 4xy plus 6xz minus y squared plus 7z squared. All right, and I can write that like so. What's the so-called matrix of the quadratic form here? I'll do the easy part. 1 minus 1, 7. That's where I pick up the, you know. Now let's see here, 4xy. So I kind of want to have like a 2xy and a 2yx, right? So I split that, and I put a 2 here and a 2 here. Technically speaking, right? I could keep this over here, and I could just put like a 0 here and a 4 here, yeah. But we don't want to do that, you know. We want to keep it symmetric. And then this 6xe, I'm going to put a 3 here and a 3 here. There is no yz, so that puts a 0 there and there, there and there. So far, so good?
Yep.
All right, so theorem. If A is a n by n real matrix and A transpose is equal to A, then there exists lambda 1, lambda 2, lambda n real numbers such that there exists v1, v2, vn in Rn with a vj equals to lambda j vj, right? And here's the kicker. Vi dot vj is Kronecker delta ij. In other words, there exists an orthonormal eigenbasis for a symmetric real matrix. So, what does that mean? So let's apply that to my example 1. So like, you know, continuing example 1, if I think about A equals to, you know, 1, 2, 3, 2, minus 1, 0, 3, 0, 7, right? Well, there exists lambda 1, lambda 2, lambda 3, such that, you know, AV1 is lambda 1 V1, AV2 lambda 2 V2, right? AV3 is lambda 3 V3, right? And so if I take this matrix, right, and I multiply by V1, V2, V3, transpose times A times V1, V2, V3, like that, what I get, the transpose of the basis matrix, when I multiply A through here, I simply get, you know, lambda 1 V1, lambda 2 V2, lambda 3 V3.
And the V1 through Vj is not a basis
For R3? Yeah. So now when I, you know, when I multiply this, I get what? I get like lambda 1 V1 transpose V1, you know, lambda 2 V2 transpose V2, lambda 3 V3 transpose V3, and like, for example, I would have V1, let's see here. Yeah, I have like lambda 1 V2 transpose V1 here. And then lambda 1 V3 transpose V1 there, etc. The point is that these are 0 because those are the dot product. It's, you know, it's orthonormal. So only the diagonals are 1, and you straight got lambda 1, lambda 2, lambda 3. So let's see here, going back to the formula we can look at it like, I mean, so this what we're looking at here, if you want me to be brief, it's like the basis matrix transpose times A times the basis matrix, right? That's what this calculation is. So if I have Q of vector x, all right, and I'll put a vector on it since I'm using x as a scalar for this example, right? Then that is x vector transpose times A times x, right? On the one hand. But I could also rewrite that as like x transpose beta transpose A beta transpose x. I'm inserting identity matrix now, because remember this right here, if I make beta for this current problem v1, v2, v3, right, that's the basis matrix, then this condition right here says that like beta, this means that the basis matrix is in fact orthogonal. And so the transpose is the inverse, you see. And so this right here is really the x-coordinate vector with respect to the beta basis times this thing. And then this is, again, that's the transpose, the x-coordinate vector with respect to the beta basis. See, because remember phi beta of x is equal to beta inverse times x, but in the current context, that's just the transpose of the basis matrix. So this is the beta coordinate vector of x. And if you look at this, if we transpose that by sock shoes, we get x transpose beta, right? So that's the transpose of the coordinate vector. And so if we just let this be, let's say, invent some new notation, x bar, y bar, z bar, okay? X bar, y bar, z bar. Then this is just straight up x bar, y bar, z bar transpose times this matrix, which we proved is diagonal, right? And then x bar, y bar, z bar. So what's the formula? Well, the formula is lambda 1 x bar squared plus lambda 2 y bar squared plus lambda 3 z bar squared. So if we can find the eigenvalues and the eigenvectors for the matrix of a quadratic form, it shows us how to rewrite the formula for it without mixed terms. The formula just has the sum of squares. And then it's really easy to answer questions about it, right? Like, if I put that equal to a constant, what is it, right? Well, if it's a positive constant and all of those all of the lambdas are positive, you're looking at an ellipsoid. Now, if I put this equal to 1, is that an ellipsoid? I don't know. But when I have that formula, and I have actually explicitly found the lambdas, then I can answer a host of questions about the quadratic form from this much preferred formula for Q. Like, this is a much better formula than the given Cartesian one. So then, of course, the question is, how do you actually calculate the lambda 1, lambda 2, lambda 3, right? Well, that goes back to the eigenvector, eigenvalue calculation, right? I have to do what? I have to work out, what's the determinant of, like, I'll do it with, I'll do the determinant of a minus lambda I, right? I'll do lambda I minus a, because that's kind of a more grown-up one. So I'm looking at the determinant of lambda minus 1, and then I've got minus 2, minus 3, minus 2, lambda plus 1, 0, minus 3, 0, lambda minus 7. Right? I got to take the determinant of this 3 by 3 matrix and I got to set it equal to 0, and I got to work that out. All right? Now we could do that if you wanted to devote 20 minutes to it. But what I'm going to do is be lazy and use a calculator. Because I just made this problem up. So there's really no reason the eigenvalues are anything pleasant at all. And so the calculation, I mean, factor an arbitrary cubic, that is a formidable problem, even for anybody, no matter how long you're in math. Like, find zeros of a cubic, unless we're just lucky, it's going to be ugly. Now, there are some things we know that we can cheat. Like, we know that the trace of the matrix is the sum of the eigenvalues. I know that the determinant of the matrix is the product of the eigenvalues times -1, I think. No, just the product of the eigenvalues. Wait a minute. Yeah, it's the product of the eigenvalues. Sorry, I had a moment of
In the statement of the theorem
thinking.
here, are we assuming that those B1 through Bn are a basis?
Man, I haven't tried this calculator in a few years. I hope it still works. What's that?
Are we assuming in the statement of the theorem that B1 through Bn form a basis for Rn? Because
Yeah, they do.
then how do we know that? Is that part of the theorem?
Part of the theorem.
Okay.
Yeah, the theorem, the real the real spectral theorem is what this is called. The real spectral theorem states that for a symmetric matrix there exists an orthonormal eigenbasis. And that means in the real sense that there are real eigenvectors with real eigenvalues.
For that.
Yeah, and they can be chosen to be orthonormal. Now tell me the matrix. Can you tell me read the top row for A for me?
Yes. For A. 1, 2, 3. Sorry, do you
Yeah.
mean the example?
Yeah, example 1, 2, 3.
Yeah. 2 minus 1, 0.
Okay.
3, 0, 7.
All right, so here I'll show you. This is a website I very much enjoy for explicit calculations like this. So as you can see, sorry to the people listening on headphones. That must have hurt your ears. My bad. A kinder person would edit that out later. I'm not that person, though. So as you can see, the eigenvalues are real. Minus 2.54, 1.23, 8.308. And here are the actual eigenvectors, numerically. So we could specifically, the formula for this is minus 2.54 x bar squared plus 1.23 y bar squared plus 8.308 z bar squared, if I use that as my basis. Now I don't want to actually do that. Like, I don't want to write that out on the board, but we could do that. Okay? And the thing is, there's nothing especially special about this example, right? This is a general technique, right? The calculation I just did for example 1, follow on, pretty much shows you that we can, I can just, here, watch. So we just take, Q of x equal to x transpose a x, and we simply rewrite that as, x transpose, it's just the calculation I just did, beta transpose a, beta transpose x, which is exactly the coordinate vector of x with respect to the beta basis. The diagonalization of A, actually. Maybe I haven't used that notation. Let me not do that. But it's precisely, assuming here that beta is the orthonormal eigenbasis for A, then that is lambda 1, lambda n, and this is, there's a transpose here, x beta. And so that is, again, if we use the bar notation, lambda 1 squared x bar 1, not lambda 1, not lambda squared, lambda 1 x bar 1 squared plus lambda 2 x bar 2 squared, lambda n x bar n squared. And here I'm assuming that beta is orthonormal eigenbasis for A with eigenvalues lambda 1, lambda 2, lambda n. All right. And I'm introducing beta transpose times x equals to x bar as my rotated coordinate system in which the formula for the quadratic form is diagonalized. Do you want me to do another example? I can do another example.
Sure.
Let me make this one small enough that we can actually hack the calculation. Let's do something like q of xy equal to, I don't know, 2x squared minus 2xy plus 2y squared. Hopefully that's interesting. So that matrix is, I got myself a 2, minus 1, minus 1, 2, like that, yeah. So there's my A, which I'm just using A for the standard matrix of the quadratic form. Notice standard matrix of quadratic form is not the same as the standard matrix of a linear transformation. I mean, we can, if you give me a matrix, it defines a quadratic form, but the way it defines a quadratic form is different than the way it defines like a linear transformation. In fact, the coordinate change property for the matrix of a quadratic form is different than it was for a linear transformation. So, yeah. You can kind of see it. Well, anyway, let me not get distracted by that, but okay, so let's find the eigenvalues of A. So we got to look at the determinant of lambda I minus A, which here is the determinant of lambda minus a 2, 1, 1, lambda minus 2, which is lambda minus 2 quantity squared minus 1, which of course is lambda minus 2 plus 1, lambda minus 2 minus 1, also known as lambda minus 1 times lambda minus 3. Okay, so then what? Well, we see that we have, is that right? They're both negative? Okay, so we get lambda 1 equals to 1, lambda 2 equals to 3. Let's actually find the eigenvectors, okay? So A minus I, let's do lambda eigenvalue 1 to start with. A minus I is equal to, what's it equal to? 1 minus 1 minus 1, 1, right? So you can easily see from this that, A minus I times the vector 1, 1 is equal to 0, 0, right? So I can just read from the, I mean, I could look at equations, but I find for these kinds of examples, guessing is far more efficient. Anyway, so my point to all this is that U1, well, I get my notation V1, 1 over root 2, because I got to normalize it, right? 1, 1. And lambda 2 equals to 3. Well, then I'm looking at A minus 3i. What's that look like? Although I would point out that you're in 2 dimensions. And so once I find one vector and I'm looking for an orthonormal basis, my choices are either to rotate by plus or minus 90 degrees. It's inescapable. It has to be either 1 minus 1 or minus 1, 1. Anyway, so let's work it out. I guess you could go either way, right? Maybe. Huh. I guess there might not be a unique choice of basis either. That's not part of the theorem. Minus 3. So I got, oh. What? Oh, minus 1. Minus 1, minus 1. Minus 1, minus 1 is this matrix, right? So this tells me V2, I can make 1 over root 2. Now, I think just as a point of like, you know, so the V1 was like this, right? This was V1, 1, 1, right? So if I want to make it sort of a right-handed basis, I would like to counterclockwise rotate it from my V1 into my V2. That would be kind of the more natural thing to do, I guess. I mean, whatever. You could go the other way, but... So I'm going to do minus 1, 1, I think, for my V2. If I do that, that will make the determinant of the basis matrix 1. If I went the other way, I'd have determinant minus 1. So like the determinant of the basis matrix speaks to the orientation, either left-handed or right-handed. But anyway, so there it is. There's my orthonormal eigenbasis, right? And so I can actually straight up calculate x bar, y bar is, I'm going to bring the 1 over root 2 up front, yeah? And so I'm supposed to take V1, you know, the right here, basis transpose, right? So the basis matrix is V1, V2, like that. But if I transpose it, I'll pull the 1 over root 2 up front, and I get V1 transpose is the top row, so it's just like 1, 1 here. And I get the minus 1, 1 down there, I believe. Right? And we can check it out. We can check it, right? Make sure this all works. We can actually verify these formulas in this case. It's kind of fun to do it. X plus y. Like if you have a really good calculus book, like a really good one that's really doing its job, you should actually have the formulas which are unraveling this for students without doing the linear algebra. Like there ought to be a section on rotated conics and how to unravel the formulas for rotated conics without actually doing the linear algebra. If you find a really good calculus book, you'll actually find that in there. I don't think you'll find it in Stewart or any really recent edition of anything, but it is in Anton's calculus from like circa 2000. Not that I know that stuff, I've never taught it, but you could teach it to like an honors high school class or something, you know, like how to understand these terms. That's the fussy part. Okay, so anyway, we've got x bar. Oh, rats, but actually what do I need to fix the formula? I need to solve for x. I actually really want the formula, what I really want is xy equals to, you know, so if I solve for x, I get this times x bar, right? Because beta matrix times its transpose is the identity, right? So I get that, you see. And so that's 1 over root 2, 1, 1, minus 1, 1, x bar, y bar, which tells me that, oh man, apparently x is equal to 1 over root 2 x bar minus y bar, and y is equal to 1 over root 2 of x bar plus y bar. Now those are actually what I want to like double check our results here. See, because that tells me explicitly how to change from the Cartesian coordinates to the rotated ones, the so-called eigencoordinates, right? And so now I can try that out. I can try it on for size, right? I can calculate q bar, if you like, of x bar y bar, which would be 2 times, I square my x, right? So I got x bar minus y bar over root 2 squared, right? And then minus 2 times x bar minus y bar over root 2 times x bar plus y bar over root 2, lots of root 2's in here, and then plus 2 times y bar squared, which would be x bar plus y bar over root 2 quantity squared. So beautifully, all the root 2's go away, right? They're all gone. And what you got? So this first term gives us a x bar squared minus 2x bar y bar plus y bar squared. And then I get a minus x bar squared minus y bar squared. Notice that the cross terms there cancel, right? In the middle one. And then over here, we get a plus x bar squared plus 2x bar y bar plus y bar squared. And as you can see, those are gone. And what should we got? We got ourselves, these two guys would be canceling, so we get, in short, x bar squared. But these add 1, 2, 3 plus 3 y bar squared. And of course, we had lambda 1 equals to 1. We had lambda 2 equals to 3. There you go. That's how it all works together. I just don't want to actually put that into practice on my 3x3 example, right? Because that's tough. Now, if I'm careful, if I'm judicious in my choice of the 3x3 matrix, it can make a reasonable test question for like linear algebra or something, but I have to be, I've got to be careful. And it does come with a high cost for students who make a single mistake in their determinant calculation. Oh man, so much carelessness in linear algebra with students who just calculate a determinant like willy-nilly, and then they go try to find eigenvectors. They find that the only vector is 0, and it doesn't occur to them, my determinant calculation is wrong. Like if the only vector you get is the 0 vector for your eigenvector, that means that's not actually an eigenvalue. That's what that means. But the subset of linear algebra students who can see that in the heat of battle, they are few. Okay, they are few. So let me. Oh, Dr. Wang is excited about something. Let me take a look-see at my notes here for a second. By the way, I just love that, you know, what's the word? Lagrange multiplier example, like the Uber example we did at the end of last class. Like I think it's so neat. I just, man. Oh, okay. So there's a little bit more theory I should mention here. The rest of the theory is more just kind of obvious stuff. All right. So to put one obvious thing I should do with this example is say, okay, so what if you've got z equals to, what if you've got z is equal to q of xy? Can you tell me what that is? Or how about q of xy equals to a constant, right? Can you tell me what that is? Well, see, those questions become easy to answer if I just use the nice formula, right? If I put this equals to z, what are we looking at? Well, we're looking at something that basically, you know, it's like an elliptical paraboloid, right? It's got, you know, whatever. I mean, its cross section for a fixed z is an ellipse, you know, it's an ellipse. And so you just got a stack of ellipses that have a parabolic profile. It's an elliptical paraboloid. On the other hand, if I look at x bar y bar equals to c, well, what is this? if I was to write, my eigen-coordinate directions like so, so there's my x bar, and there's my y bar, right? Well, I've got x bar squared, right? And y bar is a little bit bigger, right? So when x is equal to 0, a little bit smaller actually, 1 over root 3. My bad. I should write it like this: x bar squared plus y bar squared over 1 over root 3 squared equals to 1, for instance. That would be an example of what I'm trying to do here. So actually it's a little bit more like that. They're tilted ellipses, right? And if the c is less than 0, there's no solution, but otherwise you're looking at rotated ellipses. So deciding what kind of level curves I'm looking at is completely exposed by the spectrum of the matrix. The spectrum is the set of eigenvalues. If the spectrum is positive, you're looking at a paraboloid which opens up. All right. If the spectrum is negative, you're looking at a paraboloid that opens down. You'd have like z equals to minus x squared minus 3y squared, something like that. That would be a downward opening paraboloid. On the other hand, if you have a mix, if you've got one positive, one negative, that would be like a hyperboloid. If you had z equals to x squared minus y squared, that's a hyperboloid. And on the other hand, over here, my level curves would be like hyperbolae. Now, if one of the eigenvalues is 0 and the other one's non-zero, then you're looking at like a parabolic trough. If you look at z equals to q of xy, it would be like a parabolic trough. On the other hand, if I think about the level curves, I would have like a family of parabolas. And so we can visualize all these special cases, and that's what I do in my notes. Let's look at these. Oh, one more thing. One more thing I should do theoretically here before I forget is, okay, so I've given you the path for how we, let's say, diagonalize a quadratic form. You take the matrix, diagonalize the matrix, that is the path to so-called, this right here is the diagonalization of this quadratic form. Okay, that's what we mean by that. So my question, what I want to point out to you is a little bit more general, which is that if you have a quadratic form on Rn, all right, then we can make a following calculation. Let's make another calculation. Set aside the problem of diagonalization for a second here, and let's just notice something. X is equal to the norm of x times x hat, where x hat is the unit vector in the direction. So for x not equal to 0, right? We can define x hat to be x over the norm of x. So it's almost a tautology, except that that's good notation. You can calculate the length of x hat, and what do you get? Length of x over the length of x, which is, by properties of the norm, the absolute value of 1 over the norm of x times the norm of x, also known as norm of x over norm of x, also known as 1, assuming, of course, x is not equal to 0, right? Any vector in n dimensions can be written as the product of a magnitude times the direction, where we can take the direction to be a unit vector. Okay, great. So then what? Well, a quadratic form. Well, there's much to say here then, because q of x, right, is what? It's x transpose times the matrix. I'm going to use A for the matrix if you don't mind, because I get tired of writing bracket q. So check it out, right? That is exactly equal to, the magnitude of x times x hat transpose A magnitude of x times x hat, right? In other words, that's the magnitude of x squared times x hat transpose A x hat. which, in terms of the Q notation, is precisely the magnitude of x squared times Q of x hat. So what does this mean? What does this mean? It means we have a theorem that we can write down here. A quadratic form on Rn, right? It is uniquely fixed by its values on the unit n sphere, right? Theorem. Q from Rn to R is uniquely fixed by its action on the n-1 sphere, which is going to be just x in Rn such that the norm of x is equal to 1, right? And what I mean by this theorem is exactly this calculation, right? If you give me, for example, what do I mean by this theorem? Let me just try to explain it more fully. Given Q tilde, right? A mapping from Sn minus 1 to R, right? Can you extend that? If you're going to extend it, right? What is Q of, what is Q of x equal to? Well, it's equal to, the magnitude of x squared times Q tilde of x hat. And that makes sense because x hat is necessarily an element of the n-1 sphere. Now you might say, oh, hold on a second. So this defines what? This defines Q from Rn to R such that what? Q restricted to the n-1 sphere is just equal to Q tilde. This is kind of like that linear extension theorem I talked about earlier, except it's not a linear extension, right? Because this thing is not linear. It's apparently homogeneous degree 2. You see, you've got this, if you've got Q of Cx, you're going to get C squared Q of x, yeah? So that's not the mark of a linear map. And to be fussy, you should say, hey, hold on a second there. That doesn't hold for any x, right? I said it defines, but you should pick at me. That's not quite the whole story. What else do I need to tell you? I mean, that formula works for any x for which x hat is defined, but there's one for which x hat is not defined. 0, right? And what should Q of 0 be?
0.
Yeah, there you go. So problem solved. Okay? So my point to you is just that to understand the quadratic form on Rn, it suffices to understand the quadratic form's action on the unit n sphere. Right? Now the beautiful thing about this is there's many interesting things you could say about a quadratic form then, because the unit n sphere has a very beautiful topological property that this is what? This is in fact compact. It's a compact subset of Rn, right? And since that's a compact subset of Rn, and since Q tilde is necessarily a continuous function on a compact set, what does that say? Well, we have the extreme value theorem, right? It has to attain a minimum and a maximum. And in fact, you can prove the real spectral theorem scratching this itch. Like some of the proofs of the real spectral theorem will be analytic in nature. You can actually exploit the fact that you've got a compact set of Rn, and so the minimum and the maximum of this quadratic form, they're necessarily the eigenvalues. See, because if you look at it, Q tilde, right? Q tilde of like x bar 1, going back to my other notation, right, a second ago, it's going to be lambda, lambda 1, well, lambda 1 x bar 1 squared, right? So the whole diagonalization thing I did, we can still just restrict that formula to the unit n sphere, right? But here's where it gets interesting. What are choices of eigencoordinates on the unit n sphere? Like, think about the 2 sphere, for example, right? If this is x bar, this is y bar, this is z bar, these points are precisely, in the bar coordinates, 0, 0, 1, or 0, 1, 0, or 1, 0, 0, right? Using x bar, y bar, z bar coordinates for a second. So what is that? What is q tilde of, 1, 0, 0? Well, it's lambda 1. What's q tilde of 0, 1, 0? Well, it's lambda 2. What's q tilde of 0, 0, 1? Well, it's lambda 3. And you see, you can't have any of the x bars larger than 1 because it wouldn't be on the unit, because the equation for the unit n sphere in the bar coordinates is simply, x bar 1 squared plus da 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 plus x bar n, right? X bar n squared equals to 1. That is the equation of the n minus 1 sphere in the eigencoordinates. So you see, if I'm looking at q tilde, I'm only allowed to choose n tuples which have at most 1 in any coordinate, right? And you can prove, in fact, that the minimum value on the unit n sphere is the minimum eigenvalue, and the maximum value on the unit n sphere of q tilde is the maximum eigenvalue. And it's fairly obvious that if that's the way it goes on the unit n sphere, that's the way it goes everywhere. See, because this formula right here says that q of x is equal to magnitude of x squared times q of x bar, right? So if I want to find the maximum, if I want to make this as big as I can at a given distance from the origin, I want to find the direction which corresponds to the maximum eigenvalue and follow that out to that point. What I'm trying to say is, like, if I have, for example, this is like, lambda 3 is max eigenvalue, right? Then if I'm trying to find the maximum of, like, I'm trying to find the maximum on this, like, disk of radius 10 or whatever, ball of radius 10, well, it's going to happen there. That's going to be where it happens if that's where, 0, 0, 1 is where the maximum eigenvalue was. So this is why a lot of times we put the eigenvalues in order from smallest to largest, and we call it the spectrum. The spectrum is the set of eigenvalues put in order, all right? By the way, it's a very interesting and complicated question. If you're not working over a field, if you're working over a ring, what's the spectrum for a matrix? That's like a really challenging question I don't have a full command of yet. Yeah, like when you're not working over a field, the way the eigen story turns out, it's much, much more nuanced because of the appearance of zero divisors. Like, so much of the eigen story is based on the fact that, like, when you have a product of things, there's 0, one or the other of them has to be 0. Like, what if zero divisors also enter in? That just, it opens a whole can of worms that we don't really study in the regular coursework. But I've studied in some depth with students in the past on the research, but we're just not like, I don't have like a total command of that material. I have examples to illustrate the weirdness, but yeah, anyway, this is quadratic forms. So in short, to figure out where if we have a formula which is a quadratic form, we can figure out where the maximum is for it and where the minimum is for it, simply by calculating the eigenvalues and picking the largest, picking the smallest and the largest. That would be the minimum, that would be the maximum, right? So, yeah. So this is important because we're going to talk about multivariate power series, and we're going to see that the quadratic form naturally appears at the quadratic order. So if we have a power, if we have all of the first derivatives are 0, that would be a critical point, and then the formula for the multivariate function will be completely dominated by the quadratic form. So understanding whether a quadratic form is minimized or maximized that's everything in terms of deciding whether a function of many variables is minimized or maximized. Oh, I almost forgot. I was showing you some pictures. These, I would ordinarily show a projector, but as we have discovered in here, this projector is, well, it's unwilling. Let me go to my very low-tech slide projection system. I think it works, give or take. Probably should adjust the zoom length on this thing. Give me a second here. Since we're more at like 4 feet. There we go. Turn off the lights. I think that'll help some. No, 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 I didn't want to do that. Oh well. That stupid thing's going to come on in a second here. All right, so here's just some terminology. If all of the values are negative, it's said to be negative definite. If all the values are positive, it's said to be positive definite. Otherwise, it's non-definite. And we can, as I was just saying, we can determine that by simply looking at the spectrum. All right, so here is a picture of the quadratic form x squared plus y squared. It's a straight up paraboloid. All right, and there's nothing much to see there. These are dumb examples. Here is x squared minus 2y squared. That's what the graph z equals to that looks like. It's a hyperboloid. Go up one way, you go down another. It's a saddle point. I don't know anybody who would want to ride that saddle, but whatever. This is q of x equals to 3x squared. That's a parabolic trough. Let's see here. Here is q of xyz equal to x squared plus 2y squared plus 3z squared. As you can see, I've drawn some level surface of the ellipsoid, so you can kind of envision that. It's a family of ellipsoids. Now, this is what I just worked through with you, like eigenvalues and eigenvectors and such. Here's one. I don't have a picture for it, so we don't care about it. Here's another one. I'm trying to find the ones with pictures. So we just worked out this proposition 6.2.15 in here, right? If I'm not blocking the camera. If I'm blocking the camera, that would really be dumb. But it might be. That is almost the example we worked. Almost. Or is it? This might be exactly the example we worked, actually. Holy cow. I just made that up. Oh, I think that that's not right. Oh, rats. Wait a minute. Oh, I think I've got an error here. The error is pretty simple. This should be a root 2, and these should be root 2s. Because we worked out it. See, I thought, well, I was thinking if I factor root 2 out from one column, and then the other, that gives me 2 of them. But that's wrong thinking. We need the same number in every component of the matrix to factor a number out of it, right? Duh. Okay, here's a picture, if you dare, of the, the ellipse rotated 45 degrees. It's, you can kind of see it. By the way, the website that I made these pictures with is dead. It died the death of when the Java thing died. A lot of websites died with the Java. It's annoying, but so unfortunately some of the websites I made pictures with are no longer existing. Here's that one. So what you're looking at here, I start I started with a quadratic form, which is not obviously something. Like, to start with, 4xy, like what is that? Well, if I look at the eigenvalues, I find out eigenvalue plus and minus 2. And then in the rotated coordinate systems, it's minus 2x bar squared plus 2y bar squared. So it's clearly a hyperboloid, which wasn't obvious in the original system. So that's kind of it. Now this one here, it wasn't obvious what it was in the original one, but after I change it, it becomes clear. It's just, well, if I set it equal to a constant, it'd be ellipsoids. And they're tilted ellipsoids, as you can see a picture there, rotated ellipsoids. So anyway, that's pretty much what this, this allows us to do. And after the break here, we'll talk about the second derivative test. So thanks, everybody.